Hello everyone, in this experiment we'll be looking at a digital to analog converter. Just like the remaining experiments, we'll be interfacing it using 8085 microprocessor, using a study card and a trainer kit, and using a ET-DAC module, which is a digital to analog converter module. So now we'll try to understand the aim of the experiment. The primary aim of the experiment is to understand how digital data generated by a microprocessor can be converted into an analog voltage signal. This is because just as we have seen in the previous experiments, the microprocessor can produce data only in 0 and 1. It cannot produce any kind of analog data. However, in our real world, most of the systems that we use require some kind of continuous voltage. For example, the AC current, in AC current, we use a voltage that varies like this. And then there are many other examples like this. A device is specifically required to translate this digital data into an analog quantity, and that specific device is known as a digital to analog converter. It takes a binary input value and produces a corresponding analog voltage which is proportional to that number. What it basically means is, let's say the digital data is reduced, the digital data that's going into the DAC, that means the analog data is also reduced. Also, we can, from this experiment, we can understand how an 8-bit digital value can be translated into a proportional analog voltage. Because this 8-bit digital value will be in binary, we'll be looking at how it can be translated into a continuous analog voltage. Also, of course, we can understand how the 8085 microprocessor can be interfaced with 8255, which is our programmable peripheral interface. Now we'll look at the apparatus that was used for the experiment. So this that you can see right here is the study card microprocessor trainer kit for 8085 manufactured by Excel Technologies. And this one here is the DAC interfacing module. Apart from this, we have also used 26-pin FRC cables and connecting wires, and also an oscilloscope. An oscilloscope is what we actually have used in this experiment to generate the pulse or the voltage, analog voltage, which was received from the experiment. And this oscilloscope was used to visualize the output. So now we'll look at what resolution and quantization means. Resolution means the smallest change in analog output voltage, which corresponds to changing a single bit in the digital input. So since we have an 8-bit microprocessor, we have 8 bits that can be used at one time. Since we can use 8 bits at one time, the highest number that we can represent would be 256. Let us say the highest voltage is 8 volt. Then a single bit change would result in 8 by 256, which is around 31 millivolts of change. Quantization refers to approximating a continuous analog value using discrete digital steps. For example, if we have let us say an analog value like this, we would actually discretize it by sampling it and then quantizing it. That's what quantization means. Resolution and quantization is necessary to determine the accuracy of an analog signal generation. Now we look at how to interface the digital to analog converter with 8085 through 8255, which is a programmable peripheral interface. Our 8255 port must first be configured as an output port in the experiment, and this can be achieved using this command. This is a assembly language mnemonic, MVIA75H. This means the data 7FH is moved to the accumulator, And out 00H, what this basically does is it displays the contents of the accumulator in this port address, which is a port in the 8255 PPI. This value 7FH appears in the DAC as input pins because these pins are connected to the programmable peripheral interface, and that is connected to the DAC, and the DAC will convert this data into an analog signal. So this is the main flow diagram. We have an instruction and it goes to the accumulator, and through the out instruction it goes to the output port and then to the DAC and to the analog voltage output. We'll see how exactly this works in the next slide. So these are the pin diagrams of 8055 and 8255. You can see the address bus. These are the higher order address buses. They specify which port is being accessed. The address lines help us to select the 8255 chip using address decoding logic. When the correct address appears on these pins, the decoder activates the chip select pin on the 8255. And you can also see these lines, which are address lines multiplexed with data lines, which these are the ones which are used as address lines using the first part of the machine cycle. And there is an address latch enable, which is used to separate the data lines and the address lines. When the data is sent to 8255, the binary value actually travels through these lines, and this data will eventually be sent to the DAC. So you can see the data pins of 8255 here. So these data pins are connected directly to the 8085's data bus, and they transfer digital data between the processor and the 8255. When the out instruction is used, then the data is sent to these one of the ports of the 8255. So when I say port, there are actually three ports in 8255, which is 0H, and then we have 01H, and we also have 02 and 03H. Out of these, 00H is called as port A, and this is port B, and 02 is called as port C, and 03H is the control register. These are the four internal registers of the 8255. And for example, let's take port A, which is 00H. You can see port A here. So this is connected to the digital input lines of the DAC, which, as I explained, is here actually. Yeah, these are the digital input lines of the DAC, and the port A is connected to that. So when a microprocessor writes a digital number on port A, it would directly appear on the DAC input. For example, you can look here. This is the DAC input, and this would directly receive anything that was received by the programmable peripheral interface, which would have received the information from the 8085. So what actually happens is the 8085 executes an instruction and loads a digital value into the accumulator, and then from the accumulator it is sent to 8255 using the out instruction, as we saw earlier, and then this data travels through the data bus, and then it reaches port A, which is 00H, and after receiving going to port A, these are connected directly to the input lines of the DAC, and the DAC now converts this binary number into an analog voltage, and this output voltage will be visible in the oscilloscope. And we'll now see how these different waveforms are generated. For example, consider a ramp waveform. What the program does is it increments the digital value from 00H to FFH, because 00 is the lowest number that can be used, and FF is the largest digit that can be used. but using an 8-bit microprocessor. And since the digital value increases linearly, the output voltage increases linearly as well, which would look almost like a ramp. Actually, we will not get a complete ramp function. We will get something like this, but then it would be close enough. Actually, we'll look at that as well. And to generate a square wave, we need something like this. So as you can guess, we just need the program to alternate between the highest value of highest output voltage and the lowest output voltage, which can be which logic can be written in the code. And for a sine wave, as you can guess, we need to generate a lookup table, which the program can use to map to and finally generate a sine wave, because a sine wave doesn't look as simple as a ramp or maybe as simple as a ramp or a square waveform. So we need lookup tables for generating a sine wave. So now we look at the program logic of the ramp function. The first step is MVI-A80. It is to configure the programmable peripheral interface. This loads the accumulator with the value 80H, which represents the control word for 8255. And this configures 8255 in mode 0. Mode 0, which is the basic input or output mode. In this configuration, the ports simply behave as digital input or output ports without any interrupt features. These are the ports of the 8255. Yeah, and the instruction 03H sends this control to the control register of the 8255. As I explained earlier, there are 3 ports. 03H is the control register, and this control word is sent to the control register. After this, the ports of 8255 would be properly initialized. This is necessary because the ports of 8255 must be configured as output ports before they can send digital data to the digital to analog converter. Now let's look at the ramp function. So the ramp then starts from 0, 0, which is the lowest value, and then it sends this value to the port A, which is again represented by 00H, and the DAC then receives this value, which is 00. Since there are 8 pins in the DAC, it would receive 0, 0 about 8 times, basically the binary number 0 for an 8-bit number. And after this, it produces the minimum analog output voltage, which is 0 volts. So the ramp waveform begins at the lowest voltage level. Then INR is increment. The value stored in accumulator is increased by 1, and each increment changes the voltage by approximately 5 by 256, because our reference voltage in this experiment is 5, which is about let's say 20 millivolts. 20 millivolts. After this, we have another instruction which is jump 2006. This forces the program to go back to the instructions stored in 2006, where out 00H is located. This basically creates a loop in the program. After the accumulator is incremented, the program jumps back and sends the new value to DAC. Then the accumulator is incremented again, and the process keeps repeating. This is finally what happens. The sequence of digital values sent to the DAC would be something like 0, 0, 0, 1, 0, 2, and it would just keep on incrementing. Since the accumulator is 8 bits, the maximum value is FF. So when increment A increments FF, which is the final hexadecimal 8-bit hexadecimal number, what happens is it wraps around due to 0, 0 automatically because of overflow. So the output voltage gradually starts becoming FF, and then it starts going, it goes back to 0. which would finally then create a ramp waveform. Now let's look at the program for the sawtooth waveform. This, as I explained earlier, is just to initialize the 8255. Then the next step is LXIH to the 2028, which is setting up the lookup table. This holds the HL register pair with the address to the 2028. This address actually corresponds to the starting location of the lookup table. Lookup table. And as I explained earlier, in a sine waveform, a lookup table is used because the values are not trivial, like incrementing or going back and forth like a square waveform. So in this lookup table, we have not included the lookup table in this video, but the lookup table would contain values like 19, 33, 4C, and other hexadecimal integers. These are used to actually plot the analog signal in the oscilloscope. Then MVIC was to initialize the counter. This register acts as a counter, this register C, it acts as a counter that determines how many values from the lookup table will be used. Because each time a value is output to the DAC, the counter is increased. And when the counter reaches 0, the program stops reading values from the table. Because we are using a counter, this would make it easier for the program to process a fixed number of waveform points before resetting the signal all over again. And this step is to copy the data stored in the lookup table and load it into the accumulator. This represents the first voltage level of the waveform. Each subsequent iteration then reads the next value from memory, producing higher voltage levels. You can see this instruction out01. This sends the contents of the accumulator to the port B of 8255. For example, when the digital value reaches the DAC, it is converted into corresponding analog voltage. The voltage level, of course, depends on the binary value of the input. For example, if the binary input is 19, then it would be quite low. It would be low voltage. If we enter FF, then it would be high voltage. So then you can see that's basically what happens in this. And then we call delay. Then after we call delay, we increment the values in h by 1, and then we only do the same steps again and again here. This, as I explained earlier, is jump 2004. It goes back to the instructions stored in 2004, and then we repeat them all over again. That's what happens in sawtooth. And for the square wave too, it's the same. As I explained earlier, we initialize the port and then MVI A00 out 00. Then the lookup tables, which would contain two values here, and we call delay to generate the waveform. Now let's look at the waveforms and the videos which were recorded in the lab. So as you can see, this is the video. Now let's play it. This is the fuzzy cable. I just entered G2000 here, as you can see, and then I pressed Shift and 4, which then caused the program to execute. You can see a sine wave here, which doesn't actually look much like a sine wave because of some fluctuations. I entered the lookup table of sine wave, and then this is the output that I actually received at that time. There could be many reasons behind this. For example, it could be some kind of insufficient delay between the output samples. Because while generating a sine wave, a sequence of digital values are sent, which are stored in a lookup value. If the program runs very quickly, then the DAC output changes very quickly. The oscilloscope may not display a perfectly smooth waveform and may show such small distortions. It could also be because of electrical noise or poor grounding, because these disturbances can appear as fluctuations on the sine wave. Also, One more reason could be imperfect lookup tables, but then I verified it many times using one more kit and it worked perfectly in that. So it's probably not a problem of the lookup table. And also, since we are using a capacitor for filtering, that could be one of the reasons that the output is not perfect. So let's watch the rest of the video. I'm just trying to change the scale of the wave, but it really did not change anything, to be honest. Now let's look at the next video. So this is the interfacing kit, as you can see here, the dual DAC card, and this is the microprocessor kit. So these are some more minor fluctuations which I recorded. So you can see here G2000, and then a ramp wave function is created. As you can see, it appears in small steps, just as I explained earlier, because it's not very perfect, because we use the increment function. You can see the ramp here very clearly. Now let's look at other waveforms. So, and after pressing G2000 and shift and 4, you can see the sawtooth waveform here. This was what I explained in the code earlier. And this is again nothing but some other arbitrary function whose lookup values I just typed and then generated. This kind of combines a sawtooth and a square function, because it stays constant for some time at the top and then it goes down, and then the program loops all over again. And this one is the square waveform. So I just tried to change the scale of the oscilloscope in the middle. You can see how this can be used as a duty cycle as well. And that's it. So thank you.